Let's go over this problem. There were a couple of sneaky transformations on this sheet. So let's just quickly go over equations for f of x, g of x, h of x, and j of x. So let's start with f of x. That looks like kind of my parent function, right? Now, when I'm looking at that, it's a restricted domain. X is greater than or equal to 0. It's concave down. It certainly looks like a square root function to me. But we can just check that by looking at some points. When x is 1, y is 1. So far, so good. Let's pick another nice point. 4, 2 looks like a nice point. Oh, when x is 4, y is 2. Sure, the square root of 4 is 2. So far, so good. I'm convinced, but let's look at a third point. When x is 9, my y is 3. Yes, so f of x is indeed the square root of x. Or we can write that as x to the 1/2. All right, so let's maybe look at h of x next. H of x is this green thing. I think we can see it hasn't been shifted left or right. It has not been shifted up or down, but it's certainly been dilated. It's been stretched. Now, there are a couple of ways to determine this. One is just to compare with your original parent function, f of x. So in my original parent function, I went over 1 and up 1, oink. In this stretched h of x, when I went over 1, I went up 3. It looks as though my y value was multiplied by 3. Let's see if that's borne out. When I went over 4 in the original, I went up 2. Now in my h of x, when I went over 4, instead of going up 2, I went up to 6. Sure, my y was 2 and now it's 6. So I'm quite certain that the y value would be multiplied by 3. All right, let's see what this looks like then. So here we have f of x, which was, we decided, the square root of x. And of course, if instead you prefer writing it in kind of its power function form, you can think of that as x to the 1/2. H of x, we just decided, was 3 times that square root of x because each y value, each output was multiplied by 3. And of course, you could write it that way. Now, there's another way to have determined that 3. We could just eyeball it. But the other way we could have done it is we could have said, all right, I know h of x is some number times the square root of x, right? I know it's dilated by something. So you can actually plug in an actual point on h of x. So I think that we noted that when x was 1 on this new function, my y was 3. So if you want, you can just put in the 1 for your x. You can put the 3 in for your y, which in other words is your h of x, and solve for a. So let's see, a times square root of 1, well, square root of 1 is 1, so I get a equals 3. Oh, so I know that this a is in fact a 3. We could have also done that just with another point. I think, let's see, another point that we saw on h was, wasn't it 4, 6? When x was 4, y was 6? Yeah, so let's see if that works here. So my 6 is my y, or my h of x. A is what I'm looking for, square root of 4. Square root of 4 is 2. Divide both sides by 2. Oh yeah, my a is 3, right? Fantastic. Let's do g of x next, this nice brown one. Okay, so we can see that it was shifted to the right and shifted down. Shifted to the right and shifted down. So to the right 4 and down 1. And that looks like that's been dilated also, right? Remember in my original, when I went over 1, I went up 1. And this one, when I'm going over 1, I'm going up 1, 2. Ooh, it looks as though my y values have been doubled. So let's put that all together, shall we? So here is g of x. Here are all the ingredients. X minus 4 represents going right 4, because I had to put in a 4 to create a 0, which shifts the whole thing, right? We decided that the graph was dilated. Each y value was doubled. And then I subtracted 1 from each y value. That's what shifted the graph down. So 4 to the right, all the y values are doubled. So the graph is stretched. And then I shifted down 1. Now let's pretend we weren't able to figure out how to find that too. Should we use our other strategy that we used before? Yeah, let's do it. Let's find a point on g of x that we can use. So let's see, here's g of x. Let's find a nice point. Now I'm not going to use this point for -1. Well, you can try it and see what happens. I think you'll discover you get something that's true, but not useful. So let's try this point, 5, 1. 5, 1. Let's remember that. That's a point we are going to use to find the A, the dilation factor. So let's give this a whirl. Let's pretend we weren't able to figure out that A. So I'm going to substitute 5 in for x and 1 in for my y. Remember, h of x is just a fancy way of writing y. So let's see, I have 1 equals a times the square root of 1, which is 1 minus 1, and so a is 2. Da, 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 da. I just discovered using another strategy that was a 2. How cool. Math is just the best, isn't it? Now, also, of course, I could have rewritten this using different notation. So let's do that just for fun. There we go. There's another way of writing g of x using an exponent instead of the square root. Those are interchangeable, of course. All right, we have one more to look at. Let's look. J of x. All right, J of x looks like the whole shebang was shifted left 3. Ooh, it wasn't shifted up or down, but it was reflected over the x-axis. So all the y's that were positive became negative. Is that stretched at all? I don't know. Again, in my original, when I went over 1, I went up 1. Here, when I'm going over 1, I'm going down 1. No, I don't think it was stretched. I think this was just reflected over the x-axis. So here's j of x, right? We shifted the whole graph left 3, which meant which means I have to plug in a -3 to get a 0 instead of a 0, right? And that shifts the whole graph to the left. And this negative then negates all the y values. So all the y values that were positive are now negative. And of course, I also could write j of x rather than using kind of this old-fashioned square root notation. I can use a nice exponent. Okay, I hope this helped.